Hey guys, it's Mr. Lewis here. Hope everyone's doing well, staying safe at home. Today we're going to continue our exploration of the gas laws, how gases behave under different conditions. Previously we talked about temperature and pressure. So temperature and pressure were the temperature is the average kinetic energy in a gas. How the different things how gases are affected as they speed up, slow down. And more importantly, this is the big take-home lesson for that one, was that we want to measure everything in Kelvin with gases and not in Celsius. Next, we talked about pressures, and you remember we have different pressures. There's a standard pressure, which is at 1 atmosphere, and we can convert that into kilopascals, torr, millimeters of mercury, pascals, whatever you need to. There are some different conversion units that you can do, and we'll kind of refresh our memory as we go along with this. So today we're going to focus right now on looking at two particular gas laws. The first two we're going to look at are Boyle's and Charles' law. So the first one, Boyle's law, deals with how gases behave when you have a fixed temperature. So how does pressure and volume, how are pressure and volume affected as we do that? So right here I have up on your screen, you should be seeing a gizmo. This is the gizmo. It's called gas laws gizmo on, it's actually Boyle's and Charles law gizmo on explorelearning.com. I will post that into your Explore Learning accounts. You don't need to do the assessment questions. I'm not going to collect those. If you want to try them, great. If you want to play with the gizmo, great. That could really help you look at it. But we're going to play with it together right now. So we're going to focus right now on keeping our temperature. You can see over here on the graph as a constant, and focus more on changing our mass. So as we add mass to the top of this, top of the cylinder, this is where our gas molecules are, we get a change in pressure. So more gas, more mass, then you can see the pressure increases. So as I increase my pressure, what's going on with the cylinder? It's getting smaller and smaller. So as you're pushing down on the top of that cylinder, you're actually reducing the volume of the gas. And that's what Boyle's law states, is that as we, see here I've graphed it out, as we increase pressure here on the x-axis, our volume on the y-axis is going to decrease, which means we have an inverse relationship. It means that as one increases, the other is going to decrease. Mathematically, what that means is that we can create a constant of pressure times volume, giving us that relationship. So as we, I'm going to switch to a different screen here. And you can see this is also be posted into Schoology. This is kind of an graphic organizer I've built for you guys. So Boyle's law basically states, for a given mass of gas at a constant temperature, the volume of a gas varies inversely with pressure. So as I increase my pressure, my volume is going to decrease. As I increase my volume, my pressure is going to decrease. And so here we have this pressure times volume is going to equal a constant K. That constant is always going to be a little different. What we can say is that P1, V1, so P1 and V1 are our initial pressures and volumes, will equal P2, V2, our final pressures and volumes. So how does that work for us? So you can see mathematically, if you know three of those, you're going to be able to figure out the fourth. So let's get some practice with that. So I have here a sample word problem, and I'm going to show you how you should be working these out. So you can see pressure of 1 liter of a gas is increased from 1 atmosphere to 2 atmospheres. What's the new volume? So when we're doing this, you should create a variable box. And so I always start one, push one button on my pen, P2, V2. All right, and you can see, we can see here, we have an initial volume of 1 liter. So let's just go ahead and put that as 1 liter. And we can see we have two different pressures. So since we're only seeing pressure and volume, we know this is a Boyle's law problem. And our initial pressure increase from 1 atmosphere. So our initial pressure is 1 atmosphere, and our final pressure is 2 atmospheres. And our final volume, we do not know what it is. So again, if you look at that organizer, we had P1 V1 equals P2 V2. So now let's just plug in our numbers. 1 atmosphere times 1 liter equals 2 atmospheres times V2. Divide both sides by 2 atmospheres. And we get some canceling out. So our atmospheres cancel out. We're left with only liters. So V2 in this case is going to be 1 over 2, or 1 divided by 2 is 0.5 liters. Fairly simple. It's just a plain, easy ratio proportionality problem. So let's look at another one, a little more complicated. Second. All right, so again, now let's look at this one where we have a pressure of 3 liters of gas is changed from 2 atmospheres to 360 torr. So if we're looking at this, we can see we have volume and we have pressure, so must be a Boyle's law equation. So we have P1, V1, P2, V2. So my initial pressure is 2 atmospheres, and my initial volume is 3 liters. Easy enough. My final pressure is 360 torr, and my final volume is our unknown in liters. So first step, we have all of our variables, but there is an issue. Let's look at this. We have atmospheres for pressure 1 and torr for pressure 2. We want to have everything. This is the reason I like to have variable boxes. It lets me really quickly see what I have as my knowns and whether they are going to work. Well, atmospheres and torr are not the same, so we need to convert from one to another. I just tend to find it easier to work with atmospheres. It doesn't matter which one you convert. I can convert atmosphere to torrs or torrs to atmosphere, but I'm going to go ahead and do torrs from torrs to atmosphere. So I'm going to have 1 atmosphere, and this is, again, was given to you previously, is 760 torr. And it's also, this conversion factor is on the organizer. So 360. So if I take 360 divided by 760, I end up with 0.47 for atmospheres. All right, fairly simple so far. So now we can just plug in. So we now have atmospheres, our volumes. So P1 V1 equals P2 V2. Just move this over a bit. Oops, there we go. So we have 2 atmospheres times our volume is 3 liters. That's a little messy. Let me just fix that. Okay, so again, we have 2 atmospheres times 3 liters equals 0.474 atmospheres times V2. Divide both sides by 0.474 atmospheres. Our atmospheres cancel out. We're left at V2 equals 3 times 2 divided by 0.474 gives me a grand total of 12.7 liters. Hope that helps. Seems fairly simple, and you can see as we can see here that we've gone from 2, just kind of double checking here, we've gone from our 2 liters, which is a decently high pressure, to less than 1 liter, so a much lower pressure. So our volume we should expect it to go up, and in fact it does. So that kind of helps us answer that question on whether we got it right. All right, let's go back over to our gizmo. I'm going to go ahead and reset everything. So now let's look at Charles' law. So Charles' law tells us that we have a proportionality between, I'm going to switch this out, between volume and temperature. So in this case, I'm going to change our temperature. 273K happens to be, so we're looking here at Kelvin, happens to be 0 degrees Celsius. So we're not going to change mass, we're only going to be changing our temperature. But you can see as I change my increase or decrease my temperature or increase my temperature, I am changing the volume of that gas. Let's start kind of low, let's say at 50, and I'm going to record that. 275, and you can see it's going to go up. Let's just go ahead and make a bigger jump, 150. You can see we're getting good jumps, and it's a fairly linear, direct proportionality. So it means that as one goes up, the other one increases, and that continues all the way up. If I go all the way up to 500K, you can see we get a pretty good straight line relationship. So going back to our organizer, you can see here that we have, not sure, which one is it sharing? There we go. You should see the organizer again. So Charles' law states that the volume of a fixed mass of a gas is directly proportional to its Kelvin temperature if the pressure is kept constant. So again, when we kept our pressure, we kept the pressure in here the same. We did not change the amount of mass on top of here, and all we did is change the amount of temperature going into heating up the gas or decreasing, so changing that. So how does that work if we're going to do a, back to my whiteboard, a word problem on this? So let's look at this one. All right, the temperature in my refrigerator is 4 degrees Celsius. If I place a balloon in my fridge, that was initially at 22 degrees Celsius and a volume of 0.500 liters, what will the new volume be when it is fully cooled? All right, so we are looking here at, just color this up, we have a temperature, we have another temperature, we have, let's just change this to a different color, and we have a volume. So this is must be a Charles law, so we don't see anything else. Our pressure must have stayed the same, so we can ignore pressure. We are looking at volume 1, temperature 1, and volume 2, temperature 2. And remember, so Charles' law, if you look at the organizer, says V1 over T1 equals V2 over T2. And that's actually direct proportionality. So V1 here in this case was 0.500 liters. Our initial temperature is 22 degrees Celsius, because remember it says initially. And volume 2, we do not know what that is. And we'll have that in liters. And our final temperature will be 4 degrees Celsius. All right, so one of the things we need to make sure of is that when we are talking about Charles' law, we are focused on Kelvin. So gases do not like, if my temperature had dropped below 0, it makes our calculations kind of funny. We don't like negative numbers. We can't have a negative volume. So we do everything in Kelvin, where the lowest temperature you can get is 0 Kelvin, absolute 0. So we can now plug these in. Or actually can't plug these in until we convert our Celsius into Kelvin. So remember, our conversion factor is 273, or 273.15, but I'll just stick with 273 for right now. 273 plus 22 gives me 295 Kelvin, and 4 degrees, that was a terrible, 4 degrees C plus 273 gives me 277 K. So now we have the appropriate units for our temperatures. We have liters. So we can go 0.500 liters is my V1. T1 is 295. Okay. We do not know what V2 is. Temperature 2 is 277. Okay. We multiply both sides by 277. Okay. We cancel these out. Get that. So we now multiply that out and we get 0.5 times 277 divided by 295 gives me a final volume of 0. We have 3 sig figs here, so 0.469 liters. If we'd used Celsius, you'd have seen a much more drastic change. Because really the change here, 295 to 277, is not a huge proportional change, but 22 to 4 is a big change. So if we had done it with Celsius, you'd have seen this at 0.09 liters, which is a huge change and would not be the correct answer, which is why we convert to Kelvin. So in this case, our final answer is this. Hope you find that to be fairly straightforward for both Boyle's and Charles' law. I have included a worksheet in Schoology, so please check that out in the assignment below this, where you will go through and answer the questions, just doing some simple calculations. All you need to post is there's a text box, you hit click here, and it allows you to go in and plug your answers in, and then eventually submit them to me. I only need to see the answers. These are simple calculations for now. I will post an answer sheet as well, so look for that below, but please, or look from later, but please try to do these on your own first. So I hope that kind of gives you a certain introduction into our gas laws. These are our 2 easiest ones. We'll talk about Gay-Lussac, which is dealing with the other change in variables, and then finally combining all those into one big thing. And again, we'll get practice on those. We'll do those for the second part of this week. And then next week, we'll get into Dalton's law, the ideal gas law, which is kind of the fun one. Allows us to get into stoichiometry, and then finally Graham's law. Again, if you go back into our organizer here, you can see, so I have Boyle's, Charles, Gay-Lussac's combined, Dalton's law. If you go all the way down here, you can see I've also placed abbreviations, what standard conditions are, 0 degrees Celsius, which is 273 Kelvin, 1 atmosphere. And all those standard conditions also contain, hey, the conversion factor. So 1 atmosphere is 760.0 millimeters mercury, which is also 760.0 torr, same thing, which is also 101.325 kilopascals, or 101.3, or 101,325 pascals. So you can see the equations, and we'll get into more of these as we get further on. So we will stop here. Hopefully everyone's doing well, and if you have any questions, again, you can just shoot me an email, or we will have office hours on Friday as well, so you can check in with me if you want a face-to-face or anything like that. Anyways, talk to you guys soon, and have a wonderful week. Bye.